Okay, right. So in the last class, we started seeing about the motor programming model and optimization model. And we started seeing some of the problems which comes because of it, right? So the first problem we saw was that there is a intention that if the brain thinks it can control the muscle. And we saw that when we are maintaining a posture, the aim or the intention of the brain is to prevent movement. So if you are producing a movement at the same time, then the posture stabilizing mechanism would have to resist that change, right? So we saw the example of the dog, right? If the dog has to be in place, the rope which is holding it should be tight and taut. But if the dog should be able to move in any direction, then the rope should be cut out from the pole, right? So the surprise is if the brain is only sending a command at that time and we are standing in a posture, and then we are going to move to a other posture, right? At the same time, it needs to hold it tight. At the same time, it should leave it loose, right? So how is it possible that both of it can be done, right? So this is the first problem we saw, which is called as a posture movement problem, all right? Then the second one we saw was how does it specify force to move, right? And we were in that, we started thinking about the steps we need in order to plan, in order to produce a command, right? And I had asked all of you to just tell me what are the steps we have in executing a movement, right? So can I can you start telling me what are the steps we have when we have to produce a movement, right? The object is there. I've given a situation where, right, we have a glass which is there and we need to lift the glass, right? So can you just tell me? Yeah, can we have a like yeah, there is a glass which is there and we have to take the we have to uh, pick up the glass. So
Okay. So like to pick up the glass in front. So first, I will be doing the shoulder abduction, elbow extension, and the trunk flexion to reach like slight flexion toward forward. Then we'll reach for the glass. Then open the hand, open the finger extension.
no, what you're telling is once the movement starts, what is happening, right? My question is, what should you know in order to do that? In a wedding, we saw that if you have to distribute, then you need to have to know certain things, right? And then only you can start planning for it. So similarly, if you are going to take a glass of water, right? So what should we know first?
So the height of the glass and the amount of water that is present in the glass to know the weight of the glass.
Okay, right. So we need to know where is the glass, right? No.
Yes, sir.
Right. So we need to know that. Now, if say for example, I am holding a glass here, right? Okay. And my hand is here, right? So can you tell me what's the distance between this?
Ten centimeter, 10 to 15 centimeters.
10 or 15 centimeter. Right. So you need to know first that there is a distance and that you need to cover that, right? So once we know the distance, right? So what is the next thing that we are supposed to, the brain is supposed to calculate? If this is the distance, let's take, for example, it exactly calculates, right? Still, it's not possible, but we will have it, right? What is the next thing it has to do?
Brain has to think how to reach from this distance to that.
Yeah, right. So you need to, you have a distance, right? Once you have a distance, what is the next thing that the brain has to start calculating?
Planning to do that moment.
Yeah, it's planning, but what it should plan?
Size of the glass.
The weight.
Shape.
How much force can be generated?
Okay, how much force it needs to generate, right? So when you have to go from this point to this point, right, then it needs to calculate how much force it needs to generate, right? We are talking about reaching. Still lifting is another one, but right? So how much force it needs to generate, that it needs to calculate, right? Okay, so once it calculates, okay, I need, say, for example, 20 newtons of force, right, in order to move from here to here, okay, right? It calculates it. So now, once it calculates 20 newtons of force, right, next what it should calculate?
Which muscles has to be worked, the ranges of shoulder, elbow, and wrist movements.
Okay, it needs to know for that particular force, it needs to activate the muscle, right? Okay. So what it needs to do is it needs to calculate the total muscle force, right? But here we have 2 or 3 muscles are there, right? And all of them have to be there. So it should calculate for that particular force, how much is the muscle activity, right? And that activity, it has to start dividing between your 3 joints, all right? Your elbow, your shoulder, and your wrist, it needs to divide it. Okay, so how do you think muscle force is generated? What are the components of the muscle? How do we divide the functional units of a muscle?
Motor units.
Okay, so the muscles are made up of motor units, right? So you have so many motor units, and that's how the nervous system controls the muscle. So it needs to calculate the number of motor units it needs to activate. Right? Okay, so once it calculates the number of motor units it needs to activate, what is the next thing that the brain has to calculate? I think only when you all start answering, I think it will be able to.
How long it should fire? Because if it is happening continuously, the moment it may pass the target and go. So
Okay, but
how much time?
But the motor unit basically is controlled by
Brain.
no. What is connected to the motor unit from the nervous system?
The tracks, peripheral nerves.
Particularly the nerves, right?
Yeah.
So you have a lot of nerves, right? So to calculate how many motor units have to be activated, then you need to calculate how many nerves have to be activated, all right? So you need to calculate that, right? And then, as you said, how long it needs to be active, it needs to calculate that, right? As you said, once you start giving the impulse continuously, it will be going on, right? Now,
So what about the speed of the movement?
The speed at which it needs to move, right?
Yes.
Yeah, right? So it needs to calculate this, right? So you have so many calculations. Now, can we tell for a particular distance, say for this particular distance, if I have to take here, how much should this muscle work? How much should this muscle work and how much should this muscle work? Can I keep it constant? Say, for example, we said 20 newtons. Let's have it as around 20 newtons, right? So can I tell that this has to contribute 10 newtons, this has to contribute 5 newtons, and this has to contribute another 5 newtons?
It will vary.
May not be.
Sir?
It will vary.
It varies, right? So if the brain has to calculate, then each one of it, if it calculates and if it executes, then you can have only one robotic movement, right? But you may not be able to have a difference, right? What if when I'm going here, right, I see that there is some kind of resistance, right? My shirt is a bit tight over here, right? So it doesn't permit this movement to happen, right? So then that 10 Newton of force is counteracted by my shirt's tightness, all right? So then once it tells it, it cannot calculate it, right? So probably we see a problem here, right? So if this is the amount of distance it has to cover, right? Then the brain needs to calculate back one step the force, calculate back one step the muscle activities, and it needs to understand which muscle, how much it needs to calculate. It has to go one step back and calculate for that amount of muscle activity, how many motor units I need to activate. Then how many motor units, how many nerves I have to activate, right? How long I have to activate the nerve, right? So all these things have to be calculated, right? If it doesn't calculate, right, what happens is when we tell that the motor program is giving it, right, it might have a program, but then you see that the glass is not at the same place, right? So first time we take, next time we take, there is at least some variation, right? Then it becomes very difficult, okay, right? So that's the next problem we see with the motor programming component. All right, so we saw that, right? All right, we saw that in the motor programming model that it programs both the relative force and relative timing, but we also saw that it should calculate the absolute time and force, right? So now, right, so it needs to have all these things: information about the object, information about the deficit in movement, how much distance is there, it needs to know. Then it needs to know for the movement, how much torque or force it needs to produce and which direction, that is, which muscles it needs to activate. And then from the muscle force to torque, EMG to muscle force, neural input to for EMG, all these it needs to calculate, right? Now, right, so what happens is, if we actually calculate the time it requires for the sensory information, right, to reach to the brain, and then it needs to carry through the first and second order neuron to the thalamus, second to third order neuron to the cortex, right? Or if you're having a visual sense, similarly, you have a particular pathway of neurons, right? Then it has to go to parietal sensory cortex where the response has to be planned, right? Then it needs to stimulate the premotor cortex. Then the premotor to motor cortex, it needs to come. Motor cortex to alpha motor neuron, it needs to come. Motor neuron to muscle, and all the synapses and neuromuscular junction between them, right? And we know that for a nerve conduction, it conducts at a speed of 60 to 120 meter per second. And at the synapse, there is a 0.5 millisecond per synapse delay. And in the neuromuscular junction, there is about greater than 1 millisecond. Right? So now, what people have always been thinking is the motor programming modelists, they have always been thinking that if you have to program and give the exact command, right, then what needs to be there is you need to have all these calculations, right? So there should be some formula for calculating all these things, all right? Yeah. And even though there is some formula for calculating all these things, there is always a time for that formula, and then it needs to go through all these places and it needs to come out. Right? So, so that's a big problem with our motor programming theory. Okay, right? Yeah. Are you able to follow the line of thought from the previous problem? Yeah.
Yes.
So we have a lot of difficulty in specifying forces to move, right? That's the second problem we have, right? Now we'll move on to the third problem. Right? Now the problem is with the abundant choices. This is another problem which comes, okay, right? So what is this problem with abundant choices? We have already seen it, but to see that, right? Now, what I want you to do is I want you to do a simple calculation, all right? Now, we are going to take a glass, right? Here. Now, in order to take a glass, right, it is we have approximately 4 joints which altogether work, right? Now, each joint has the following possibilities for moving in multiple directions. Okay, right? For example, joint A can move in 6 directions. Okay, up, down, medial, lateral, right? And then one side rotation, other side rotation, right? So it has approximately 6 directions it can move. Right? Now joint B can move in 2 directions. Okay, right? Now you have a glass and you have to go and place it at a particular place. Okay, right? In front of us, you have to place it. Now joint B can move in 2 directions, joint C can move in 2 directions, joint D can move in 4 directions. Okay, right? So can you tell me how many possible directions are totally there in which if you are having a glass in your hand, it can move before it reaches to the target?
$98, sir.
98. Okay, right. I think Vipin's maths teacher has been very, very good, right? So you see that 6 into 2 into 2 into 4 gives you 98, right? So there are 98 different directions, right, in which we can move, right, before taking the glass and placing it at one particular point. Right? So, right. So, now, I just forgot to tell one thing. Each of these joint is at least controlled by 3 equivalently capable muscles for moving it in one direction. Okay, right? So, say for example, you want to bend your elbow, right? Then you have biceps brachialis and the other muscle, right? So you have 3 muscles. Okay, right? So now, how many muscles do you think the brain has to control if it has to move? What are the total possibilities which are there? I think you...
More than 7,000 times.
More than 7,000? From where does that come? I'm not sure about it.
No, like 3 equivalent, like 3 muscles and 4 different joints. So already he told 98 the possibility of movement.
Yeah.
So 3 in each level. So altogether it comes somewhere around 7,000.
No, we don't take 3 in each level because each level we have already spoken, right? So it probably multiplies by 3, for example, right? All right. And for each muscles, I have at least 1000 motor units, right, which can help in moving in that direction. But only 100 motor units are sufficient. Okay. Right. So when you go from the muscle to the motor unit, what we see is point with so much ease, right? When you think when you sit on the brain and when you start thinking, right, then the brain needs to start making a decision, right? If I have to move in this direction, I have to move. Say, for example, the joint can move in 6 direction, but I'm going to move in only 1 direction, right? So in all the 5 other directions, there is always a possibility of movement, and that needs to be controlled. All right. So if the brain has to work, it needs to, it has too many degrees of freedom, and it needs to control all the degrees in order to permit one, right? So, right, when I have a choice and abundant degrees of freedom, we again have a problem. Okay, right? So how does the motor program we saw last time, right? How does it specify very clearly these are the muscles which have to work, and it just activates that? So that's the next problem we are facing. Okay. So now we'll go to the next problem, right? I just want to slightly take a break, and then, right, you can just tell me any viewpoints or anything you think you can just tell.
Sir, maybe motor program is something like, it looks like an impossible to do such an fast action or variety of movements, but at least some basic motor program will be there.
No, sir, that's
if not very specific for every actions, maybe some basic motor program can be there, right?
That's what
reaching like that in general terms, probably reaching or grasping, something like some can be some set of basic rules. Is there a possibility, sir?
There should be some set of basic rules. If it is not there, then I don't think we
Okay.
are going to have a movement, right?
Yeah.
But the question is, does the
precisely, yeah, for each and every action, whether there is a motor program or not?
No, that's what we'll come to that. But these are the questions which are there for the motor program to answer, right? So when you conceive it as a motor program, then the brain should actually tell exactly so many things, right?
Yes.
So when it has to tell so many things, but when we do movement, we seem to be perfectly doing it, and we seem to be doing it without any problem, right? So,
there's also one more thing. I don't know. I'm not very sure about it, but I don't have the reference. Maybe I'll try to get it. Like one study was done. Like if you are planning to pick up a glass of water, there is already there's a motor activity happening in the brain. It has been recorded through EEG or even other methods. Like it is something related to destiny. Like everything is destiny based. Like even pick up a glass also, there is already a motor program happening, or there is a motor action happening in the brain about a few seconds ago. Something like that. One study is there. I don't know the full details. I'll try to get it. This was told by my guide, Dr. S.R. Chandra. Any action we do, before to that, there is a motor activity happening on the precise area of where that particular action is happening. So I don't know. This is something.
There will always be an activity over there, but
Yes.
I don't think we have area for drinking, right?
Yeah, not like that, but
Yeah.
hand action. So, for example, it might activate the hand. We have the area, right, in the brain. That is
Yeah.
definitely there.
So it's
That
definitely
that
there. There's
particular
no
region
question
has
about it.
been kind of activated. So, this is only, of course, we cannot precisely say that action, but there is a area facilitated, area is been activated. It means the person is going to pick up a glass has been already decided.
No, so one thing I'll just tell you, right? We are
Yeah.
not taking out the brain out of the equation.
Yeah.
We are telling there is the motor program, and we tell, right?
Yes.
People told that it's a program and there is a computer, and the computer is giving these programs, right?
Yes.
And it's telling, right, this muscle you activate, this muscle you
Particularly.
activate, this much you activate, correct? So
Mm-hmm.
that particular concept is what we are talking about.
Yeah.
You know, we are not telling that the brain doesn't act. The brain should be acting. There should be activity, right? So,
yeah.
Right? So only thing is we are just seeing what are the problems that are being posed to it. Okay, right?
Yes.
I think we are able to logically connect it, and we are able to understand, okay, this might be a problem.
Yes.
Now, the next theory, whether it's giving a solution to everything or not, is a different thing. But first, we need to understand that there are difficulties, right?
Yes.
Okay. So, yeah. So I'll just go back to it, and then we will sit with more problems from which we can't get up. All right. So now, when we are trying to move, right, we have many objects which are there in our environment. And when an object is being moved, right, if you say, for example, you are going to push a particular object, right, then the object will move a certain distance, it will stop, right? That's the rule. That's how it goes on, right? And if we are leaving an object at a particular level, then what happens is it falls down at a particular speed, right? So now what we see is any physical object which is there, that has to actually that has to obey certain laws, right? And we call that as Newton's laws, right? Now, when we are trying to move a human being, right, then that one, right, whether it obeys Newton's laws, if it obeys Newton's laws, right, then it should not be obeying neural laws. That is, if I'm telling go faster, right, than what it is, right, then it should not be obeying that. Clear? All right. So there is always a confusion between whether the movements are controlled by neural laws or Newton's laws. Okay, this is the next problem which was being posed. Okay, so let's just go back to our physics class and start thinking what are the laws. Can you tell me the laws? Newton's three laws. Yeah.
The first law is if I'm right, maybe if there is an object which is at rest, it continues at rest. If we are moving it, it will keep on moving. These two, like unless until external force, unbalanced force acts on it, something like that.
Okay, I think you have sat in your physics class and you have come over here, right? That was perfectly all right, right? So unless and until acted upon by external unbalanced force, right? So object to move, external force has to be there, and that has to be unbalanced, right? Only when we see our humans, right, we seem to generate auto movements, right? We ourselves move ourselves, right? So is it possible that, say, for example, if we are drowning in a quicksand, or if we are drowning in a water, just to hold the air and lift ourselves? I don't think it's possible, right? So yeah, that's one. Okay, right? So that's perfect. So if you need to move any object, living or non-living, to a target location, you need a right amount of external unbalanced force acting on the body. All right. The force produced will move the object unless and until acted upon by an opposite force. And if no force is acting, the object should not move. Right. That's what the first law has told. Right. Now, what is the second law?
That force is equal to mass into
acceleration. Okay, that's great. Right. So any object can be made to move faster or slower by increasing the force acting on the body. Right. The acceleration is directly proportional to the force and inversely proportional to the mass of the object. That is, at what speed it's moving is directly proportional to the force with which it is being pushed and inversely proportional to the mass of the object. Acceleration due to gravity will pull the object down if a force does not pull it in the opposite direction. So that's your second law, right? And I hope we don't need to speak about the third law. Of course, everyone will be very familiar with that, right? So it's fine. Right? Now, the problem, what happens is we don't go to school to learn how to move, right? Because to learn the three laws, we need to go to school, and we spend a lot of years till we don't get it right? But then we don't go to school to learn how to move. Only when we start walking, we start going to school. Okay, right? So if that is the case, then either we should be performing all movements wrongly, right? Since we don't understand Newton's laws. So if our brain is trying to somehow control it, it needs to basically fight against the natural forces, right? Because we seem to not obey the basic rules, right? So the example they give is if you leave a toy frog on a table, it will not move. But if you leave a live frog, it will move off. Okay, right? So unless an until acted upon by an external force, it should not be moving, right? That's the rule. But a living frog moves, right? So what basically they are trying to tell is when you are going to control a particular movement, right? Then there are forces from the external world which are controlling that, right? And from the internal, you are also controlling the movement, right? So you have two things which are there, right? Now, how do these two things come together, right? Now that's again a problem, right? Because if the brain has to calculate the force and all those things, it needs to understand Newton's law, right? So that's what we see, right? So on one side, if you see our movements, we can place an object exactly where we want, right? That is, we can move it and we can exactly place. So the first law is fine, right? We can lift a glass with the desired speed. If you do not know what is the acceleration due to gravity which is pulling, how can you lift the glass against it at a desired speed, right? So we should be knowing that, right? And then when we are placing an egg, right? You're placing an egg inside a box or anywhere, you don't break it, right? Which means that you know exactly what is the force the counteractive force will give. All right. So on one side, we are seeing that we are doing movements perfectly and all the laws are being followed, right? These are only not the laws. There are many other laws also. Okay, right? Yeah. On the other side, right? If a glass is placed in a place, it will remain its own place. But if you are placing your hand, it will not remain so, right? So this seems to act against the first law. Okay, right? If water or any object, right, will always tend to move downhill. Any object with the mass will always tend to move downhill. But we see that all the time whenever we are moving, we are always working against it. For example, we are standing up, we are moving the COG up, right? But the mass has to go down. So we are acting somewhat against the second law. We are not overcoming the second law, but we are acting somewhat against it, right? And whenever we are walking, we always hit the ground during heel strike, right? And keep doing so even though the tissue can damage, because once you hit the ground, it can give a contraction force, right? And that's going to damage the tissue, right? So on one side, we seem to follow all the law. At the other time, we also do a lot of things which could be contrary to what the law is telling, right? So how does the brain decide it, right? Because decision about this is very much needed if you want to move something perfectly and the program has to give it exactly as we saw in the last time, right? So it again adds to the problem. Okay, all right. So we have a complexity which is building up here, right? Okay. So, right. So how does our body move? Newton's control. Okay, right. So that predominantly what the motor control scientists have done. It just explains it. So both kinematics and kinetics, they only describe the movement. You should not think that, okay, how my bone is moving, my muscle is acting, so that's how my bone is moving. Okay, right? But your muscle is acting, it's creating a force. That's also another phenomena we are observing, right? We don't have a reason why it is moving like that. Right? So that's other problem with the notion of controlling the movement by a program. Okay, right? It not only needs to control whatever is there within its control, but also the external forces, how they are acting, all these things it needs to know. Okay, right? And we'll come to the last problem, right? Which is can brain control a muscle to produce a force? Okay, all right. That's the last problem. Okay, right. So, right. Now we all know that whenever we are trying to move, the muscles are working and there is a movement which is happening, and we also know that the amount of force which a muscle can take is not equal across its length, right? So you have an outer range, you have a middle range, and you have a inner range, and we always know that the middle range is more takes more resistance than the outer or inner range, right? So if you see the curve of how much force for different lengths of muscle, we see this kind of curve, correct? So can anyone explain me why the force is more in the middle part and why it's lesser in the outer and inner part?
So because of mechanical advantage in the lever system.
Length
because if mechanical advantage, if you're telling, then it should be more capable as it comes close by to the joint. So the inner range should be very, very easy, right? As compared to the middle range or the outer range.
No,
so that's the mechanical advantage.
Also one more factor is, you know, when muscle becomes short, the force production is less.
Yeah, but why?
Sir, because the sliding membrane is in optimal position, sir. It is not even in this full lengthened position. It is not in the optimal position. So the
what do you
membrane,
mean by that? Optimal position means what is the advantage of that optimal position?
sir, when it is moving closer, there will be changes in this actin myosin binding.
Yeah, the number of cross bridges are going to be more in the middle range, right? Yeah, and in the outer range, there is going to be less overlap. In the inner range, it is going to have half of it would have been used up already, and they are not going to do anything. Right? So that's what we see there. Right? So whenever we see whenever we tell about a muscle force curve, right? This is the curve we just have it, right? Now, when you see the actual length tension relation curve, that's force to the length, when we see, actually it is slightly different. It comes like this. Okay, all right. So as the length increases and increases, right, it is able to take more resistance. Okay, all right. So Senthil sir, you told me that in the inner range it will be more powerful because it's close by to the lever, right? But the actual curve, when they are measuring it, right, it seems to be just the opposite of it.
Okay.
Okay, right. So can anyone tell me what's the reason for this? What could be the reason for this?
For example, in one moment, if we take the agonist antagonist point of view, can we understand this way? Like opposite muscle will be lengthened only at that outer range.
Yeah, when you're lengthening it, no, you see that in a shorter length it's less, and as you go greater and greater, it is able to take more and more distance.
Yes,
increases. Okay, right. So what happens is what we need to appreciate here is we are capable of understanding one thing, that when your muscle is contracting, then there is an overlap between actin myosin and the force is coming, right? But when you actually measure it, it comes different. So what it basically means is there is some other force which we are ignoring, right? Am I right? Am I understandable?
Yes, sir.
Passive structures.
Okay, right. So we will go on to that, right? Why is the curve different than that of a muscle, right? What they have found is what model we have learned is actin myosin bridge. That's what we have learned, all right? But there seems to be something else. The muscles are composed of two other components, right? One is a serial component, the other one is a parallel component. What we mean by serial component is it is in line with the muscle, so it's called a serial component, and the serial component is the tendon. Okay, we all know that muscle is there, at the end of it tendon is there, right? And the parallel component which is there to the muscle is the sarcolemma or the muscle membrane. So what happens is both of these structures have a lot of elastic fibers. Okay, and what they have found is these structures are basically elastic in nature. So what do you think will happen when a substance is elastic in nature? Yeah.
It helps in lengthen the muscle.
Yeah.
Lengthen the action or lengthen the muscle.
So what happens is this is a elastic structure, right? Yeah. So when I'm just going to do this, right, it's going to give a force, right? It's going to pull me in this direction, right? So that's a force. If I'm going to pull it more, what do you think will happen to the force in this direction?
Counteract.
More.
No, will it be less or more? That's the question. I'm pulling it here, right? And I'm pulling it here, right? When will it be more?
Then
more. When the length is more, right?
More.
You see that the force is going to be way too high, right? Yeah, right. So what happens is since this is also there, right? This is the curve of elasticity, and all of us know that if the length is going to increase, you can see on the x-axis, if it's increasing, the force is also increasing. Up to a certain point, it is slightly less, slowly it's changing, and greater and greater you pull it, it's going to make more, right? So what basically happens is when your length, when you're going to move the muscle, right? So what happens is your actin myosin bridges is going to contribute to the force, and you see the curve first curve. And then when you're pulling more and more, the length is going to keep increasing, and so you have a curve of elasticity which is there. So when you combine both of it, you see that in the inner range you have less amount of force, and you go to middle range, it starts increasing. And as it starts falling down in the first curve, right? The force of elasticity increases and it contributes to it. So ultimately we are having a curve which is similar to this. Okay, right? Yeah. Right. So what they tell is there are two components to a force which can be generated by the muscle, right? One is because of the pulling of the actin myosin. The other is because of the pulling of the elastic structures, right? Now here the problem starts coming. Do you see any problem in this? By this architecture, say for example, our primary goal was to lift our hand and move it to one particular place, right? So in order to lift the glass, right? So do you see any problem here, additional problem?
I don't think so. Yeah.
Okay, right. So now what's the problem over here is we said that if you have to move from point A to point B, there is a particular force which is required, right? And the brain has to calculate this force and it has to give that force, right? Now, the brain can control your actin myosin. Can the brain control the elastic structures? Can it control the tendon?
No.
No, but it gets the information probably.
No, here it's we are not talking about the information which is going back to the brain.
Okay.
We are telling the brain is moving it, right? So it has to create a particular force, right? Half of the force is under its control. The other half is not under its control, right?
Yeah.
But when we are trying to lift it, we are going and lifting it, right? So we have a problem here. So what ultimately happens over here is, I'll quickly go through. One is when we are trying to move, the muscle cannot be controlled completely by the brain. So there is a force discrepancy. So it's going to have a lot of problem, right? Now this length also is not going to be similar across different muscles, right? So it's going to have a difficulty in doing that, right? Now, right? On top of it, there are many forces which the brain needs to control, right? If all the movements, including our bone movements which are happening, they will follow Newton's law. So that needs to be additionally controlled by the brain. Right? So that's a second problem. And then there are multiple muscles. The brain has to control all the muscles and all the forces it has to control, right? So that's a problem. And then it needs to calculate at each and every level what needs to be happening, right? And it needs to give an exact output. Okay. And motor programmist theory primarily said that this is how our brain is controlling the movement. Okay, right? So ultimately we see that there is a huge problem with the notion that the brain can control the muscles directly. Okay. If it has to control it, then it needs to overcome all these problems. It needs to have a lot of calculation going on, which is very tough for it, and it should be going on. Okay, right? So that completes the problem with the motor programming theory. All right, so I'll just stop there for some time for us to just digest and think over. Okay. If you have any questions, you can please ask me at this point of time. Sheikh sir?
Yes, sir.
Yeah, sir. So, yeah, your any inputs to it, anything?
No, sir, I'm just simulating it, and yeah, for me, I'm just wondering, like, if we feel like actin myosin can be controlled by the brain, why not then elastic structures? if that is possible to a certain extent,
Mm.
then why not there is elastic structures?
So you mean to tell it can control the elastic structures, which means tendon.
It can have an impact. If actin myosin, if that thing can be done, why not this? I'm of a little bit of not unsure about in the first place, like whether actin myosin is also this cross bridge is also whether it will be able to control. If it can control, since you had said like one part it is under its control to some extent, then why not? Then this can also be done. Why not then?
Okay, right, but we don't see any nervous supply directly to the elastic structures, no?
Yes.
And if we
Sir,
tell that
but
the bone can be controlled, we don't see again a connection there in order to do that. Right? Now, tendons, of course, there is a nerve which is going out, but a nerve which is coming in and controlling is not there. So there is an afferent nerve from the tendon which is going to the brain, but not a efferent nerve, right, to the tendon directly per se. So we don't have a connection. So when connection is not there, it is not feasible to control.
But as per the context, we can able to even if our intent was something different. For example, if I am going to reach a glass of water, but if after I have started initiated the movement, if I want to change for any reason, for example, if someone is calling me so that I have to change it, I can able to do it without much delay.
Yeah.
Then with this, can we say that the brain have complete control?
That's what, sir. And now the question is not with the brain, right? So the brain has a control, right?
Yes.
Clear. But the question is to that level of specification, how it needs to control, right? How have we overlooked all these things and we thought that okay, it was so simple. That's the question which is being raised at the present point of time, because we always took that okay, fine, it's simple. We know how the control is happening because none of our physiology textbooks talk about the elastic structures, force, or other things. It just stops there at one point of time. But the nature of it is always there. So,
yes, sir.
Selva sir, Sendil sir, others, Naveen.
It shows that brain doesn't have controls on many aspects.
Yeah.
Direct control on many aspects.
Direct control seems not to be there.
Yes.
Yeah. So if it is controlling everything, then we're really going to face a lot of problems. It's not going to be that simple, right? But still we seem to get it. Anything else from anyone?
There can be a possibility that brain, rather than a program, it has some algorithm type which it keeps modifying or updating as it started doing the movement or it started executing the movement.
Yeah, that's exactly right. The reflex model.
Yes.
Right. So that's where they said there is a closed loop control. So as you start moving, it just keeps updating, and then you're getting the right movement. If at all it deviates, it starts coming. So you told the right solution, but the solution is previously we saw that there is a fundamental problem with that solution. So
yes.
We need to now move forward. Okay. So this is the summary of the whole problem. So we all think that movement is very simple, but it has all these complexities into it. And so we require a model which is capable of doing a perfect movement. At the same time, it is capable of overcoming these problems. Okay, right. So that's what is a solution which is currently required. The solution to this model is given by a equilibrium point model, right? So I'll just start with that. We will again stop in the mid of it, and then we will again continue with that in the next class. So just start with that. Just give me a minute. Can you hear me? Is my voice audible?
Yes, sir.
Yes, sir.
Yeah, can you see my screen?
Yes, sir.
Yes.
Yes, sir.
Yeah, right. So, what has happened in the middle is we were all following things, what is going on, right? But now we see that it's getting very complex, right? Basically, one of the things is, as we said that in the first, neurophysiologists were working on that, and then the second one, the psychologists and biomechanics were working, right? Now, the solution has come from a very, very different set of professionals who are physicists. And so some amount of physics knowledge is basically required. Rather than telling a physics knowledge, we don't need to learn any formulas or things like that. But then we need to basically understand it conceptually, okay, right? In order to imagine what can be and what cannot be. Okay, right. So that's why this model is going to be quite complex, and many of us may not understand it in the first instance, but let me try and put it. And if you have any other inputs, you can please give it to me. And where you're not understanding, you can just tell it to me so we can just keep moving forward. Okay, right. So basically, the theory is called as equilibrium point theory, and it explains how a muscle is being controlled by the nervous system. So what they basically tell is the muscle is in fact not controlled directly by the brain. Okay, when we tell the nervous system, it gives to alpha motor neuron, and alpha motor neuron comes and supplies the muscle, and it supplies. But they tell that there seems to be 3 different levels at which the muscle seems to be controlled. Okay, right. Now all these three different things which are controlling the muscle, when they all come together, they all seem to control it in a very different manner from rather than how we are thinking it is being controlled. Okay, all right. So let us go one after the other level and see, right? At each level, we are just going to see how the muscle is being controlled, right? So no need to connect or confuse with that. The first one is the peripheral level, right? If you look into the periphery level, right? Now, what happens is whenever there is a muscle which is there, right? And when we are trying to activate a muscle, there are 2 things which is acting. Okay, right? One is the let's leave out the muscle per se, that is muscle contraction. No, let us leave that out, right? So say for example, you're just going to have the arm, right? You just keep your arm and you just extend your arm and flex your arm, right? when you do this, right, if you want to move from a position where your elbow is, say, extended, right, from that position, when you are going to just lift your, bend your elbow, what is going to happen is the weight of the bone and of the hand is going to add to it and on the muscles which are acting on the elbow, right? So this is what we call as an external resistance, right? When we tell external resistance, you really don't need external weight or something to add to the resistance. Just the weight of the bone and the weight of the hand itself will be adding to that, right? So on one side, this is pulling, right? You can see in this picture the load which is there on the, right? On the other side, we now saw that the muscle has elastic properties, right? So there is a elastic band which is there and it is pulled, right? So when your muscle is in, when you're activating the muscle, when your muscle is in longer length, then what happens is all the elastic structures are pulled to the maximum. Your tendon is pulled, your muscle membranes are pulled, all these are pulled, right? So this is elastic resistance. So what happens is elastic resistance is acting from internal and the external load is acting from external, right? So these two things are acting together, right, on the muscle. Okay. So this is your level A. All right. Now here we are not talking about any of the muscle contraction. We are just talking about whenever you have activation of a muscle, these two forces will be acting, they'll be counteracting against each other, and where your limb comes to rest is basically dependent on how much elastic resistance is there and how much external load is there. Okay, right?
Excuse me, sir.
Yes, sir.
Can you please explain the elastic resistance? There is you mean to say that the elastic, if I'm comparing it with a rubber band, then they can say that the rubber band is stretched, right?
Yes, yes.
It is stretched to that level. So then why elastic resistance, the term resistance, I'm not understanding there.
The resistance is the pulling force it is giving, sir.
Okay.
Okay, right?
Okay.
So what we do over here is, right? Now let's forget that there is a muscle ultimately.
Okay.
Okay, right? Yeah. Now this is there, right? Clear? If I'm pulling it, it's giving a resistance to my movement.
Yes.
Okay, right? Yeah. Now what we see is if the rubber band is just left like this, it doesn't do anything. It doesn't give any resistance to anything. Right?
Yes.
Now let me just show you one second. It has now these two structures. Okay, one is a pen, right? Let's assume that this is a object, right?
Yes.
Yeah. And it pulls, right? Now the position of it, that is where it is exactly there, right, is at one particular level, right?
Okay.
If I take this out, it goes to a different level.
Yes.
Okay. Now instead of it, I'm just going to have this, right? Clear? This object. This object is heavier.
Yes.
So here, what it's going to do is, it is going to, the position of this particular object is going to be at 1, right?
Yes.
The length is not going to be its resting length. It is going to be some other length. Okay, right? Yeah.
Yes, sir.
So what basically is happening is, if you forget about the brain, how it is controlling and everything, right? The place where it is and the length at which the muscle is can be anything.
Okay.
Right? Yeah. Now, can you tell me what will decide where this or this will be in?
Okay. The elastic property of the band.
Band, right?
Yes.
Which means, what is we call this as a stiffness, right?
Yes.
Stiffness. So depending on the stiffness, it can be in any place.
Yes.
Okay. All right. Are others also following me?
Yes, sir.
Yeah, right. We are not talking about the upper control and everything. We're just talking about periphery, right? If you cut out all the brain and you're just leaving it, right? Still, you are going to keep your muscle at a particular length and things like that. It will be resting in one particular position. Okay, right? Now this we see is not under the control of the brain, right? And it can be anywhere. Okay. No. Now we'll move on to the next level. Level B. Okay, right? Now, this is something which we all are very familiar with, but we need to just try to think about it. Okay, right? For this is level B, which is at the spinal level. Okay, and we call this level as the closed loop control level of force. Okay, right? What is this closed loop control level? Okay, right? So the red one, what you see here, right? So this one, this is the muscle. Okay, you have your alpha motor neuron, which is over here, right? You have a muscle spindle, which is here, right? And you have a tendon here, right? This is the structure of the muscle and the basic nerve, which we are very familiar with, right? Now, this spindle, which is there, all right? So it has two groups of neurons. One is this particular neuron and the other one is this particular neuron. Okay, right? So this is called as a gamma motor neuron. This is called as a 1 alpha, right? We all know that the muscle spindle's property is if the central portion of the muscle spindle, as you see here, right? If it is pulled apart, that is the central portion, if it is stretched apart, right? Then what happens is it sends an impulse to the brain via the 1A fibers. Okay, I'll just clear it for now, right? So if this central portion is being stretched, right, it sends impulses via the 1A fibers that it's being stretched, right? And what do you think will be the response of the muscle to it?
Muscle will contract, sir, through
muscle will contract, right? So basically when you're going, right. Basically when the muscle spindle is stretched, what happens is 1A goes and just stimulates the alpha motor neuron and it starts contracting. Okay, right? Now, this is what we have been commonly seeing whenever you have a tendon jerk, which we are giving. What normally happens is you hit on the tendon is being pulled. That is, it's pulled in this direction, right? So it is being stretched. So the muscle spindle is stretched. Once the muscle spindle stretches, it gives you a activation and the muscle is contracting. All right. So this is the normal one which we have seen. Right? Clear? Now, the beauty here is there is also another neuron, gamma motor neuron, which is attached to the ends of the muscle spindle, right? So if the gamma motor neuron is active, then the muscle spindle ends can be controlled. Now, the muscle spindle endings are also made up of fibers like your actin and myosin. Okay, right? So when your gamma motor neuron is giving an impulse, this particular part is going to be contracted. Okay. When it is contracted, what do you think will happen to the muscle spindle?
Sir, it will give the continuous impulses when the muscle is at rest also. Because of that only the
no, sir. No, we'll go to that, right? That's at a later point of time. Now, the thing is, when your gamma motor neuron is being stimulated, right? Clear? What will happen to the muscle spindle?
Again stretched?
It will again be stretched.
Yeah.
Right? Yeah, the center portion will be stretched if the edge of it is contracted, right? So then if it's stretched, then which neuron do you think will be activated?
Again, the type 1A fibers will get activated.
Again, the type 1A fibers will get activated and that's going to activate your alpha motor neuron. Right? So we have two systems. One is your gamma motor neuron and your alpha motor neuron, right? Both of it is when your gamma motor neuron is being activated, it's going to make the muscle contract, right? Clear? So basically what it happens over here is either the muscle spindle or the muscle which is there, right? If you're stretching it, right, it will produce a contraction of the muscle, right?
Sir, whenever the muscle is lengthening or it is shortening, whatever the length changes is there, it will be taken through the type 1A fibers. It is not only the lengthening, it is also shortening. Whatever the changes in the muscle length, whether it is shortening or is lengthening.
No, so if it is shortened, then 1A fibers will not be activated.
Sir, whatever the changes in the length, the
no. See, ultimately it is intimating about the length. Okay, right?
Yes.
But if your muscle spindle is shortening, then 1A fibers will not be activated. But ultimately it will send the information about length to the brain. Okay. Right. So,
but the function of muscle spindle, they have said is it will gives the information about the length of the muscle fiber and change in length of the muscle. Change in length of the muscle fiber and rate of change of length of the muscle fiber. How much fast it is changing.
That's what.
So length change can be whether it is shortening or it is lengthening. No, sir. Length. When it is in the rest, it is in that position. When it is changing, whether it is shortening or lengthening, it is considered as a change in length, no, sir, muscle.
No, Subbu. It's slightly complex than that. It's not just from the 1A fibers. 1A fibers will not get activated if the muscle spindle is just shortening. It will only give the information if it is lengthened.
Sir, if the gamma motor neuron is getting activated, then the shortening is happening.
Yeah.
So at that time, the length is changing. So
the length is increasing. No. That's what. At that time also the length is increasing. Right? It's being stretched. The muscle spindle is stretched and it will carry the impulses. Okay. We will just have the argument at a later point of time, but this is what happens. Okay, right? Clear? All right. So what happens is we see here whenever there is a stretch which is there, right? It can create a activation in the muscle and the muscle can contract, right? Okay. So that's what ultimately happens over here. Can you just tell me any other structure which when it is lengthened, it will start pulling?
Structure in the muscle, sir?
No, I'm just asking generally, right? Any structure you know of, whenever it is lengthened, it will start pulling it back. Yeah. Can anyone tell me any structure?
It's elastic property, sir, that you are saying.
Yeah. Right. So what happens over here is because of this particular nature of control, whenever we are going to lengthen, right, the muscle is going to pull it, right? And that's exactly the property of elasticity. Okay, right? So without complicating much further, what is happening is this second level which we are seeing, right, is called as a servo control level, or what it means is whenever there is increase in length, right, it can be shortened. Okay, right? Now, how much length, how much it will shorten, right, depends on how much your gamma is active. Okay, if your gamma is much active, what do you think will happen to the resistance which is or to pull which is given by the muscle? I just want everyone to just understand this because this is one of the basic ideas in the control. Yeah.
I didn't understand your question.
What's sir?
What's the question?
No, sir. What I'm asking is, right, because the connections are like this, what happens is the muscle which is there, it starts acting like a rubber band, right?
Yes.
When you're pulling it, it's going to contract, right?
Yes.
Clear? Now, what I'm asking is, we saw a small structure in the muscle spindle, which is your supplied by your gamma motor neuron, right?
Yes.
If the gamma motor neuron is going to be activated much, okay,
okay,
right, then what do you think will happen to this elastic nature of this?
It will reduce. It may get shortened in a it may be in a shortened position for a longer time.
It may be in a shortened position for a longer time.
Yes.
Okay, right, clear. Or how do they tell that is, if your muscle spindle is going to be active, then what happens is the stiffness property which we saw in the last time of the elastic band, right, that will be increasing. If your gamma is going to be very less active, right, then the stiffness property will loosen. Okay, right?
Okay.
So what basically happens over here is, you need to assume it. Last time I try to bring therabands. I'm not sure whether anyone has brought a theraband or not, right? But if you take multiple rubber bands, okay, 1 second, I'll just show you. Now you see, you can see these two rubber bands.
Yes, sir.
Okay, right? Clear. So if I'm going to pull them both, right, this rubber band, if I'm going to pull them, right, it will give a particular resistance, right? If I'm going to pull this particular rubber band, right, to this same length, what do you think this will be doing? It should be giving me more force.
The smaller one, the green one.
The green one is going to be giving more force.
Yes.
Okay. Clear?
Yeah.
So now, because of the servo control loop, not only the muscle, which was only doing the contractile property, became elastic in nature, right? But because the gamma is there, it can change the level of contraction which it can do to the muscle spindle. You can convert at one point of time this rubber band to another point of time to this rubber band.
Okay. Okay. Got it.
Yeah.
Yes, sir. Yes, sir.
So it's like you have different therabands, and then you can just change the theraband whenever you want. Okay.
Okay.
So that's your second level. Okay. Right. So your second level is your servo loop, which converts your muscle into an elastic structure.
Okay. Depends upon the context, how it can be, how it is needed. It can be converted. That's what you're saying, right? The same muscle, muscle can be.
No, that we will go to the next level. But at this level, the property is it becomes like elastic band, and you can change the stiffness of the elastic band.
And as per the need, yes.
Okay. As per the need. Okay, right?
Yes.
Okay. Now I'll go to the last level, and then I think we will stop over there. Right. Okay, right. So, right. Level C is the central command. Okay, right. The brain gives the command. Now, the brain doesn't give the command to the muscle. It just gives the command to the second level. Okay, right. They are providing tonic descending inputs, which means continuous inputs to level B. Okay, right. And right. So what they do is they are providing a central, right? You can see here, it gives a command to the gamma motor neuron, right? And the gamma motor neuron creates the muscle spindle, the afferents go, and then they stimulate the alpha motor neuron, right? This is called as a tonic stretch reflex loop. Okay, so what we previously saw was a stretch reflex loop. Central command can give a command to the gamma motor neuron. So if it wants, it can increase the stiffness. If it wants, it can reduce the stiffness. Okay. Right. So those are the three levels of command. Okay. All right. So I think I'll just stop here. Beyond this, if I go, it may not be understandable. So I'll just stop over here. Right. And we will see about the movement, how it is controlling, that we will see at a later point of time. Okay, because I want this particular concept to get in, then only it is possible for us to understand how the movements are happening and how a joint is being controlled, how multiple joints are being controlled. All of them are interrelated with this. Okay. So in summary, what happens is you have 3 levels of control. Okay, right. One level is the peripheral level where the elastic structure and the resistance which is given by the muscle, they both act together. They are not under the control of the brain, right? They can go anywhere, right? Second level, when the muscle wants, it can increase its stiffness or it can reduce its stiffness. Okay. All right. But the brain doesn't control the stiffness per se, but the stiffness property can be changed by the brain. Okay, right. And the third level just gives an input to the gamma motor neuron. It can also give an input to the alpha motor neuron if it wants. There is no denial about it, but it just gives it, right? So what it does is it basically changes the elastic stiffness of the muscle. Okay. Right. So ultimately, all these 3 things combined together produces the output.
Sorry, can you tell me about why you say that brain cannot control the elastic directly? That's what's happening, right? But
there are the 2 levels of elasticity. One is the passive elastic structures, which the brain doesn't have a connection to. Okay, right. And a second structure, right, which is there in the spinal cord, which it can convert into elastic-like property. Okay, right. So there is an elastic thing which it can control. There is also elastic thing which it doesn't control. Okay, right. Clear. So ultimately, from the first day, many you and some of us have been telling that the movement is an emergent property. Right. Actually the emergent property, it basically means that some part of it is under control, some part of it is not controllable. Right. So what they're basically telling is where a movement will start and where it will end, right, is not entirely under the control of the brain. Okay, right. So that is the end part of it is not under the control because there is a peripheral structure which can vary in any way, right? But the brain cannot control. That's what they mean by that. Movement emerges. Movement is not controlled by the brain when we tell it. It's basically that. It's not that entirely the movement is decided by the environment. When the environment is telling, it's giving a perceptual information. It is not doing that, right? So that's what. So we see that there is a limitation in the way we are interpreting those ones.
So if we make it an order, what it can be, the command comes from the central is the first level of a movement, and then further this peripheral structures takes over or they influence and bring about a movement, right?
Yeah, all these 3 are interconnected. So we need to see them together. We cannot see them separately or sequentially, right? So the brain doesn't.
Which part of the body to be moved? That's definitely happen with the peripheral.
That's what. That's an entirely different level. We will go on to that, right? In the next class, we will see about how individual joint is being moved by a muscle, right? Okay. And then we will go on to how multiple joints, when they are there, how they are being moved.
Okay.
Okay. Right. Yeah. So this is the most toughest part of it. If you understand these 3 components, right, then we need to do a lot of imagination in order to just understand its properties.
Right. Yeah. So the EMG property is not only by the central commands which is coming from the brain. It is the EMG output is because of the interaction of all the things, sir. The things which is coming from the sensory signals.
Yeah, I think Subbu, I think we can go slowly to that point. Okay, right. Clear. Okay. So EMG is not, because we have always learned that the brain sends an impulse to the nerves and the nerves send an impulse to the muscle and the muscle EMG, right? The number of motor units and it's controlling each and every motor neuron. That's how we have learned it, right? But then we will see how it is emerging. I think next session, Subbu and me, we will both try to explain that. Okay, right. But But this is a slightly different way of looking into it. We need to have it, then only it will be possible for us to move on and understand how the movements are being made without contradicting or without fighting against all the previous restrictions we saw. Okay, right. So this is called as a equilibrium point model. What actually a equilibrium point is, I'll tell you what is that equilibrium point, right? But you need to just visualize this. Okay. Okay. Any other questions from anyone? I hope all my students would be right. Okay, enough of it. Motor control, right? I know you would have moved out.
So can you suggest basic reading material to have a fair understanding of this before attending the next class?
Yes, sir, it is very difficult for me to suggest one because Anatole Feldman is the one who found the equilibrium point model, right? Yes. But by the time he comes on to explain this, each of this, right, it becomes very complicated because there are too many terms which comes in.
Yes.
Okay, right. So it becomes very complicated, right? Subbu sir, do you have any direct material which explains only the 3 steps and how it's being controlled? Subbu sir, are you there?
Sir, his book contains all the articles, sir, that 40 years of equilibrium hypothesis, in that it is there, sir.
In that it's there, but is there any one article which tells about this? Because I know 40 years it took for him to tell this, and so many experiments and things. It's a volume this big, 40 years of equilibrium point model. Okay. Okay. So
I will check it and I will send, sir.
Okay, if it's there, you please send it across.
Yes,
because
sir.
The way in which he has experimented and he has come to these conclusions are also very novel and very interesting, right? But before going into that, we should basically learn these smaller components. Then it's easier for us to build it and try to understand. Any of that book which we have kept it referent model, no, right? That book goes one after the other. So the first chapter, if you read, I think now it will be slightly more understandable than before, because it basically talks about Newton's control and neural control. No, that part of it, the first chapter explains it in detail.
Okay, sir. Okay.
Okay, right. So
yes.
Just read about it. Okay, right. I hope I had confused everyone to the finest extent. We will just try to have more clarification in the next part of it. Okay.
Thank you, sir.
Yeah. Thank you for all for the patient listening. Okay, right. Please digest this information. We'll move forward. Thank you.
Until now, it looks clear, sir. I think now next session only it will start. I think confusion.
Okay. Now, if you're clear till this, that's really a big achievement, because it took at least 6 years for us to really come ahead and get into terms with that. Okay, right?
Yes.
Too many discussions, we had too many disagreements, what it is and things like that, and then we just came, okay, it might be this, right? But then I think.
Thank you.
Thank you, sir.
Good night.
Thank you.
Thank you.
Good night. Good night, all. Thank you.
Yeah.